Yeah. Thank you, everyone. Thank you very much for joining in. So today we have Professor Alex. He heads the Power Electronics and Magnetics Lab at the University of Texas at Austin. So today Prof will give a presentation on his publication, a high frequency power factor correction converter with low output voltage. Please put your question in the chat and Prof will take it once in a while. Please go ahead, Prof. Please go ahead.
Okay. Well, thank you for the introduction, and actually, I'm very excited to be able to give this talk and speak with you all today. So thank you so much for making the time, and I understand it's probably reasonably late in the evening there. So thank you for making the time to listen. The as was mentioned, the paper that we're going to talk about is this paper that was published in, I think it was officially published in 2020. We really submitted it in 2019. I think everybody here probably understands why we want high frequency stuff, but we'll talk about why that's particularly difficult to get in power factor correction. And then we'll also talk about why low output voltage is a desirable feature. If it's all right with everybody, I'd like to give a brief sort of shameless plug for the university. So UT Austin is where I work. This is sort of an aerial photograph of it. UT Austin is the flagship university for the University of Texas university system. So it's sort of the main university in the state of Texas. It's one of the 10 largest universities in the country, about 52,000 students. The 2019 Nobel Prize in Chemistry went to a variety of people, but one of them was Dr. John Goodenough, who works here at UT in the ECE department for basically the invention of the lithium-ion battery, which is pretty cool. And we have a recently assembled power team, and by power I mean both power electronics and power systems. And 3 out of the 4 of us who are faculty members in this area were hired within the last couple of years. 2 of us are new professors, and then one of us, Professor Alex Huang, is a very established member of the field, and he came to us from NC State, North Carolina. Our building that we work in the electrical engineering department is called EER. It's a brand new building. It was completed in 2017. It's a very nice space that we have. This is a photograph of sort of the main atrium, sort of a nice new space. It's the lab I did my PhD in was the opposite of this. It was a sort of a crap hole in the basement of a school. So it's a very different environment for me to work in anyway.
Yeah, most power labs are like that.
I'm finding that it used to be that power electronics labs were all in the basement, and that's because everyone worked on electric machines and you wanted to bolt your machine down to the foundation.
Yes.
These days, a lot of the new power labs are being built on the top floor of the building so they can access solar on the roof.
Good.
Different environment, yeah. So the city of Austin, Texas is sometimes referred to as Silicon Hills. It's as opposed to Silicon Valley, it's kind of a second headquarters for a lot of tech companies. And this is sort of a chart that just shows many of them, but not even all of them. Many of these are semiconductor companies, but there's also systems companies. A lot of software and stuff is going on here as well. So, I mean, just about anything tech related, you name it, it lives in Austin almost as much as it does in Silicon Valley. So hence the nickname Silicon Hills. I just want to point out a couple of things that are not on this chart. I did not make this chart. There's a company called Enphase Energy, which is a leader in solar energy. That's actually the research arm anyway is headquartered in Austin. I think I got the location approximately correct. And then Tesla is also building their gigafactory that's going to be building the Cybertruck. They chose to locate that in Austin. So here's Elon Musk with Governor Abbott. This is the UT, University of Texas sports sign. But these guys are going to be located about right over here, just in Austin. And the university is, the picture they're showing for it is right here. So we're about 15 minutes from everything, which is kind of a great position to be in. My group is called the Power Electronics and Magnetics Group. I specifically called it that way because a big chunk of my group does work specifically on magnetics. So for those of you who are in the field and actually work with power converters, you know full well that, for example, the power converter I'm presenting today, even this one that's operating at high frequency and so on and so forth, still has enormous magnetic components in the main power stage and also in the EMI filter. And so, building better magnetic components specifically is a big focus of my group, and about half of my group does basically asks the question, how do you build a 10 megahertz transformer? Is sort of the summary question. And I think that focus on magnetics makes my group relatively unique. There are of course other groups that do this, but many groups do converters and then they dabble in magnetics. My group is split roughly 50-50 between sort of converter circuits and then hardcore magnetics. Okay, so power converters. Of course, I think everyone in this audience is probably very familiar with what I'm about to say. But this is a teardown of I believe this is a MacBook charger. But you can see what's going on here. You've got an EMI filter at the input. You've got most likely a boost stage for power factor correction and a large magnetic component to go with that. And then you have buffer capacitors that are associated with the power factor correction and probably this one as well. And then some sort of a step down stage to get from, most likely the output of this thing is 400 volts. And so this has to step down from 400 to usually about 19 for a laptop charger. But of course you can see here that the biggest components by far here are the magnetics, right? You've got a huge transformer here that's providing isolation and voltage transformation. You've got a very large boost inductor here, and you've got several EMI filter components. And those are taking up the majority of the space. Coming in second place is of course the capacitors, right? You've got the big buffer capacitor, and we'll talk about how there's not much you can do about that component. But there are other capacitors as well for sort of short-term energy storage. And so the motivation for this talk is the higher frequency you can operate at, the smaller, at least in principle, you can make all of these passive components. And because the passives are so dominant in the size of the overall solution, that's the thing we really ought to be targeting if you're worried about size at the same time as worrying about efficiency. So, and this is just a slide to sort of illustrate that the fundamental way a power converter works, if you strip away all the details about switches and switch configurations and how transformers work and so on and so forth, fundamentally at a very, very deep level, what a power converter does is it stores energy and then it releases energy to the output in a controlled fashion. And so, the power that you're able to process with the power converter is proportional to the energy that's stored and the frequency you operate, right? It's how much energy can you store and how quickly can you shuffle that size of energy from the input to the output, okay? Of course, you can design different power converters that require less energy storage, but there is a fundamental limit to how low you can make the energy storage requirement at a given frequency. There is a fundamental limit to that. And so if you divide power by volume, and you want to talk about power density, right? Instead of raw power, you just want to talk about power density. That would be proportional to energy density. In other words, how tightly can I cram energy into a component? And frequency, how quickly can I transfer that energy to the output? Energy density is really a function of materials. It has to do with how good is your magnetic material, how good is the interface material between your capacitor, your capacitor plates. How good is the conductor material that you make the coil out of? And by the way, if you find one that's better than copper, let me know. But at a fundamental level, energy density is really controlled by materials, and we're pushing material limits all the time. And I'm not a materials designer. I don't pretend to be a material scientist at all. So I can't directly control that. I can try to use the best materials I can find. And some of the most cited work that I have is basically just going out and finding materials that already exist that work better for magnetics. But as part of my group, I'm trying to actively work with folks who are material scientists and to help identify what is the most important stuff for us to be targeting. For me, that focuses on magnetic materials, but of course there are other materials that are needed as well. On the frequency side, though, that's what I can address with design, right? I can design a power converter to operate at higher frequency. And in principle, that sounds great, but of course, there are reasons we don't build power converters at a gigahertz, right? You need to contend with all kinds of high frequency loss mechanisms, switching loss, high frequency effects in magnetics, and all sorts of things. Not to mention, you need something that can react quickly, right? If you're going to turn switches off on and off really quickly, you need very fast gate drivers, you need very fast PWM generators if that's the kind of power converter you're building, and so on and so forth. So, but I look at all of these things as challenges, not as fundamental barriers, and that's what how I teach my students as well. I hear a lot of people talk about, well, I don't want to go to high frequency because then I'm going to have switching loss. Like, well, frequency is the only thing you have at your disposal to make your power converter smaller. So instead of saying, I don't want to go to high frequency because switching loss is going to eat me alive, figure out a way to get around the switching loss, and so on and so forth with all the other things. So I see these as challenges, not as fundamental barriers. And that's sort of the notion of the research in my group, is overcoming all of these things. So to introduce sort of the topic that we want to talk about today, we're talking about power factor correction rectifiers. So you have the grid. Okay, here's my grid voltage from the wall. And a very, very typical architecture for this would be to run this through a diode rectifier into a power factor correction stage. And so without drawing what this PFC looks like, suffice it to say that the PFC needs to draw current from the input that's proportional to the voltage. So the voltage you expect to see here is kind of this rectified sinusoid. And so the PFC has to draw current that's also a rectified sinusoid and in phase. Because of a variety of reasons, this is typically implemented as a boost converter. And so the output voltage has to be higher than the peak input voltage, okay? And so if you're designing something to have what's called universal input, or in other words, you can plug it into any grid in the world, the highest voltage you expect to see on any grid in the world is about 375 volts when you account for a 10% margin, okay? And so you expect to see up to 375 volts on this rectified sinusoid. Therefore, the output of a boost converter would have to be at least that high, right? And so people usually put this at 380 or 400. At a certain point, it doesn't matter that much. And then you run this through some sort of a DC-DC stage to drop it down to whatever you're trying to get to. If it's a laptop charger, you use 19 or 20 volts, sometimes 12, whatever the application asks for. But very few applications actually want 400 volts DC at their input.
Yeah.
So the typical solution is a boost converter. And one of the reasons for that is that you can have an inductor at the input. And so you have at least continuous current at the input, which makes it easier to filter. And because there are stringent requirements on how much EMI you're allowed to put into the grid, having at least a continuous current at the input is very nice, instead of a chopped, sort of a chopped current. The main competitor I see to the work that I'm about to present you I would consider to be the valley switched boost converter, okay? So the idea of this is it's a boost converter that's operated approximately at boundary conduction mode, okay? So the inductor current goes up when the switch is on, it comes down when the switch is off, and then right at this moment when the inductor current hits 0, the diode turns off, and you actually have a third state where both the switch and the diode are off, and you get a resonance between the inductor and the parasitic capacitance that Wikipedia doesn't draw in here. Okay? And that resonance here is what gives you this little shape to the inductor current. And what does that do? It allows the inductor has negative current, right? So the inductor is pulling charge off of this capacitor and reducing its voltage, okay? And depending on the voltage conversion ratio of the boost converter, the parasitic capacitance voltage may or may not be brought all the way down to 0, okay? And that's kind of what I'm showing here in this graphic at the bottom. When the output voltage is bigger than double the input voltage, okay? Or in other words, as long as the input is less than half of the output voltage, This resonance effect here will in fact bring the switch voltage all the way down to 0. And so you can then turn the switch on with 0 volts across it. You get what's called 0 voltage switching, soft switching, and you radically increase the efficiency of your converter. And more importantly, you eliminate a form of loss that scales with frequency, right? So if you can make that loss 0, then you can operate at 100 kilohertz, a megahertz, 10 megahertz, who gives a crap, right? You can go as high as you want, within reason. Of course, what I just said, that rule is violated when V in is more than half of the output, okay?
Yep.
So if my output voltage is 400 volts and my input voltage is 375, I'm violating that rule pretty strongly. And it turns out that, because the typical output voltage is 400, if you draw a 220 volt RMS sine wave, it looks like this. And you spend an awful lot of time up here in the red zone, right? Not getting 0 voltage switching. And in particular, the closer you approach to V out, in other words, near the peak of this, not only do you lose ZVS, you lose it by a lot. Like you're getting barely any benefit from the valley switching here. Okay, so this is what I would consider the main competitor to what I'm about to present you. And this is one of the big challenges with it, is it cannot get 0 voltage switching in this very important voltage range, okay? So going back to my overall architecture, that's what lives inside this PFC here. And because the valley switched PFC, even though it can get 0 voltage switching sometimes, it can't get 0 voltage switching all the time, which means you have to operate it at reasonably low frequency. Okay, so a lot of these converters are operated at 90 kilohertz, 100 kilohertz, maybe 140 kilohertz, because that's just below the EMI cutoff. But typically in the 100 kilohertz range is the limit, is how fast people tend to operate these things. And a big piece of that is what I just showed you, is the fact that you don't reliably get ZVS in all applications all the time, okay? The other thing that I see as a challenge to this is it's sort of a bizarre thing that you're doing, right? You take a low input voltage, you boost it up to 400, and then you buck it back down to 12, right? And even if you didn't know anything about power converters, even if you'd never studied this before in your life, if you just had some basic engineering sort of insight, you would sort of think to yourself, well, that's gotta be bad, right? I'm paying something for all of these conversions, and going up and then down again, I've got to be paying for that somewhere. And in fact, you are. What ends up happening is you're asking this DC-DC stage to have a huge step down ratio.
Yes.
And anyone who's actually designed power converters knows full well that the steeper the conversion ratio, the trickier it gets to build the stinking thing. So this is my cartoon for a stressed out second stage. So this is sort of what I want you to keep in your minds is the whole system matters, right? So if you read a paper that's like, oh, I designed a really awesome power factor correction converter, that's awesome, right? But if that stage is making the next stage have a harder time, that may not show up in the paper because they're just writing the paper about that power factor correction stage. But what I want you to keep in your mind is this is a whole system consideration. And this is where the low output voltage part of my talk title comes in. We're going to build a power factor correction converter that'll do all the wonderful things that the boost converter does, plus it'll get 0 voltage switching, and so we can operate at higher frequency, plus it'll output a voltage that's not 400 volts, but probably something more like 200 volts, okay? Or even as far as low as 100 volts if you're able to. So that will generate a benefit that I can't show you because I didn't build a second stage. So I can't show you that benefit, but trust me, it would show up if you actually designed a second stage, and we'll see that in a minute.
Prof, we have a quick question. Can we just take it before we move on?
Yes, I can, but I appear to have screwed up my thing here. But yes, I can absolutely take a question.
Nachiket, please go unmute yourself and go ahead. Okay. Yeah. Please go ahead.
Hello. I hope you are able to hear me.
Yes. Please go ahead.
Yeah, Professor Alex, the question is asked from the power rating viewpoint. So the question is that is the valley switch to boost PFC, will it have always higher power density than a PWM boost PFC. It is purely from the power viewpoint. So the things which we are talking about are probably maybe 100 watts or less.
So you're asking is
Applications such as EV chargers where they go till like 2 and 2.5 kilowatt.
so let me make sure I got the question right. For the first part of the question sounded like, will a valley switched PFC always have higher density than, for example, a continuous conduction mode PFC? Is that?
Yes, yes.
Yeah,
That
that is the question, yes.
Okay. The answer is, as always, is it depends. Okay. So for example, if you had a valley switched boost PFC that always got zero voltage switching, okay, so if you knew that you were always going to operate in this input voltage range, then you would be free to operate at much higher frequency, right? Instead of operating at 100 kilohertz, you could operate at 2 megahertz and you get a factor of 20 benefit in energy storage. And so in principle, I would think that you could get better energy density or better power density out of that. However, as we're seeing here with the power factor correction converter, even the valley switched boost PFC does not always get ZVS, which means you're not free to increase your frequency to 2 megahertz, which means you don't really get much of a benefit out of from the power density. You may get a little bit of efficiency improvement because you do get zero voltage switching as long as you're in this range, but you can't just build it to operate at 2 megahertz because up here you'll blow up your MOSFET basically. There are, of course, other things that come into play. So I don't want to just cast this as a frequency is all that matters thing. So for example, a continuous conduction mode PFC has the benefit of very little AC current at the input, right? The current is almost DC, it just has a little bit of ripple in it. And so EMI filtering is easier there. And so you can have a smaller EMI filter in principle. But there's sort of, the EMI filter also gets better with frequency, so it does depend on a lot of things. How you would compare a 100 kilohertz CCM converter versus a 2 megahertz valley switched or like the weird converter I'm about to present, that's a little bit more of an interesting question, right? This one benefits from low ripple at the input and maybe a smaller EMI filter, but this one benefits from really high frequency, which benefits both the EMI filter and the main power stage. So hopefully that adds a little bit of clarity. The one other thing I'll say is that if you're doing perfect power factor correction, which is what I'm going to assume this presentation, the output capacitor, the buffer capacitor, has to buffer the 60 hertz or 50 hertz line energy, not just 100 kilohertz energy. So the big buffer capacitor in a PFC is actually immune to frequency. It doesn't change with operating frequency. So in like a DC-DC converter, I expect things to get a lot smaller with frequency. With the PFC, because it's got this big anchor component that doesn't get smaller with frequency, there is a limit to how much better you can get. I hope I answered the question.
Nachiket, I hope if you have any follow-up, please go ahead.
No, I think that's it. Thank you.
Yeah, you can give just a brief intro to Prof, what you're working on so that he knows your background, just one line.
Yeah, Professor Alex, I'm working on
Yeah, I think audio cut out.
the exact thing that you actually mentioned, the anchor component. So here the idea is to replace the 100 hertz filtering capacitor with the active component and a very small value of capacitor so that the energy utilization will be better.
Okay.
So yeah, that's fantastic.
Yeah,
I have friends who have worked in the active buffering space. Absolutely. Yeah, that's been a really promising area. So congratulations. It's a very cool project, I think. And if you're, I'm sure you know the references that I would send you, but I'm happy to send you some references of stuff that I'm familiar with anyway afterwards, but I'm sure you already have them.
Good. Thank you, Nachiket. Prof, we have one quick question. Somebody is asking, can you please reiterate why ZVS happens at V out by 2? They missed it. That went over.
Yeah, so yeah, unfortunately, I didn't actually show on here why this happens, but if you analyze it's a very simple circuit to analyze. If you analyze a voltage source with an inductor and a capacitor, that's all it is. It's just an inductor and a capacitor. And we're analyzing this resonant period. And the initial condition, capacitor's initial condition is that its voltage starts at V out, right? Because this is just after the diode turns off. The diode was conducting, the capacitor, the parasitic capacitor right here, its voltage was V out. So the moment the diode turns off, the capacitor's initial condition is V out. The inductor's initial condition is 0, right? Because the inductor current starts at 0. So it's a very simple circuit to analyze. It's just a voltage source, an inductor with an initial condition of 0, and a capacitor with an initial condition of V out. Just analyze what happens to the capacitor voltage in this very, very simple resonance circuit. And unfortunately, I'm not showing it here. But if you analyze that and you write an expression for the minimum capacitor voltage, okay, you'll get an expression, and you'll see in that expression that if V in is less than half of V out, that number is less than 0. And so you're capable of getting true ZVS. But if V in is greater than half of V out, you'll get some number that's not less than 0. It's a positive number. And therefore, you might be getting some benefit, but you're not getting true ZVS. So I'm sorry I didn't show that on here, but it is a pretty simple circuit to analyze. Good homework problem.
Yeah, thank you. Yeah, please go ahead. Yeah.
Sure. Okay, so let's see. We got a stressed out second stage. We're trying to get high frequency. All right, so here's the deal. Here's what we want to build. Here's the crazy idea that I propose to you, okay? It's a 4-switch buck boost converter, and here's how we're going to operate it. I'm going to first set SA1 and SB1 to be on, okay? So it's just the same as the boost converter, actually. I'm just connecting the inductor from the input to ground. And so because I have the input voltage across the inductor current rises. Actually, so far, this is exactly the same as a boost converter. Then what I'm going to do is I'm going to turn off SB1 and turn on SB2. So now current goes from the input through the inductor to the output, and the output voltage is higher than the input. So this is my slope, it's V in minus V out, and the inductor current starts to fall. And actually, this is still exactly the same as the boost converter. So far, there's no difference with the boost converter. But here's the weird thing that I'm going to do now. I'm going to interrupt this by turning off SA1. I'm turning this off, okay? I turn off SA1, and I turn on SA2, okay? Now I've got the inductor connected from ground through the inductor to the output. So I have minus V out is going to be the slope, V out over L is going to be related to the slope of this thing. And the inductor current is going to fall, and it's going to fall pretty rapidly down to 0. But now look at what happens. When the inductor current finally falls to 0, this device, we're going to turn this device off, and we're going to turn this device off. It's going to be everything's off, nothing's on. And all we have are these parasitic capacitance here. These are just parasitic elements. I'm not putting in any capacitors, but I've drawn them explicitly. But I want you to notice that we have a resonant circuit just like we had before, but it's a different resonant circuit with different initial conditions. In this resonant circuit, it's a CLC as opposed to a voltage source LC, okay, which is what we had before. And the initial conditions for this are that this capacitor starts at V out, but this capacitor starts at 0, okay? And actually, this is an even easier circuit to analyze than the other one. If you analyze this circuit where one capacitor starts at V out and the other starts at 0, I know exactly what the minimum is going to be because the capacitors are just going to exchange voltage. This one's going to ring down to 0 and the other one's going to ring up to V out, okay? So I know that the voltage at node B should ring all the way down to 0, regardless of what V in or V out is, right? Regardless of what V in and V out are. Node B will ring all the way down to 0, and node A will ring all the way up to at least V in and theoretically all the way up to V out, although that won't be true because of the body diode. So what does that mean? That means that node B will go all the way down to 0. That means I can turn on SB1 again, right? Remember our first state was having SA1 and SB1 on, so I want to turn those devices on. I can turn on SB1 with 0 volts, regardless of the input voltage. This is a boost mode, so the output voltage has to be higher than the input. But regardless of the input, this will get ZVS, even for that red range that I was showing before. Similarly, node A will ring all the way up to, well, theoretically all the way up to V out. But again, because of the body diode of this device, it won't actually reach there. But it'll reach at least as high as V in, right? And so if node A rings all the way up to V in, SA1 should be able to turn on with 0 volts across it, right? And so if you analyze each and every one of these transitions, there's basically, 3 or 4 transitions here. At every single one of these transitions, every single switch gets 0 voltage switching, okay? And for these power levels, we really care about 0 voltage switching much more than 0 current switching. So every single device on every single transition gets 0 voltage switching, okay? And that's for any V in less than V out. And it is a boost converter, okay, in this mode. So what does this allow me to do? This means that if I'm clever enough and if I'm willing to do the work to make this thing operate in different kinds of modes, I can do all sorts of fun things. One is, if I set the output voltage at 400 volts, I would have that graph like I had before, but I can use the boost mode when the input voltage is low, and I can use the modified boost mode when the input voltage is a little higher, and I can get 0 voltage switching over the entire line cycle, right? And therefore, I'm allowed to build my converter to operate at several megahertz rather than 100 kilohertz. If I'm even more daring, right, I can set my output voltage not at 400 volts, but something like 200 volts, right, if I'm even more bold. And then during the line cycle, I can start with the boost mode. I can, as the input voltage gets a little higher, I transition to the modified boost mode. And then as the input voltage gets above the output voltage, I can transition to a buck mode. And I didn't prove it, but if you analyze the buck mode will get 0 voltage switching as long as the input is less than double the output. So as long as I'm not going to more than double the output, the buck mode will also get ZVS. So, and this is really the thing I'm proposing, is this triple mode of operation. And this power converter can do it all, right? It'll do all of those operating modes. It always gets 0 voltage switching, and I can set that output voltage down at like 200 volts rather than 400 volts, right? And as I mentioned before, that doesn't necessarily benefit this stage, although I do think it actually does benefit this stage. But more importantly, it benefits the invisible stage that's coming after this that I'm not drawing, right? It's a factor of 2 benefit. People publish whole papers on how to get a factor of 2 better power, conversion ratio, right? So I'm getting you a factor of 2 for free.
Great.
Okay. So how do I actually make this happen? It's simultaneously more complicated and simpler than it looks. So this is not a pulse width modulated converter. I want to be specific about that. This is not a converter where you can just say SA1 and SB1 and SA2 and so forth, just turn on and off in a certain order. You have to have something watching the circuit and looking at when the switches get ZVS to make sure they turn on with 0 voltage switching. Especially during this resonant time, you have to have something sitting there watching and saying, for example, either watching the current and seeing when the current hits 0, and then waiting for a little bit. That's what a lot of converters do. They let the current hit 0, and then they wait a little bit, and they figure, okay, we're close enough to ZVS. Or you can actually sense the voltage directly, and that's what we're doing. So on any of the switching nodes, right, there's 2 switching nodes. On any switching node, I step that down because my comparators can't measure 400 volts. But I step that down, and I run this into a ZVS detector, right? It's just a comparator, just a simple comparator. So when V switch gets below a certain threshold, I say, oh, hey, cool, the voltage is coming down, we're ready to go, let's go. And so this comparator sends a signal that goes out through, it turns out a NOR gate is useful for this, you can analyze that, but it sends a signal that says, hey, it's time to turn the device on, we have 0 voltage, yay, right? Time to turn the device on. And that's what turns the device on. This same signal, the same signal that tells the device to turn on, also comes down here. And this circuit looks complicated, but it's actually very simple. This is a current source. This is just meant to be acting like a current source, right? This is a current mirror. So this is meant to be a current source into a capacitor. So this is a ramp generator, okay? It's a ramp generator with a reset. So this same signal that tells the main power MOSFET to turn on also begins a ramp, right? It lets the ramp go. And the ramp ramps up, it ramps and ramps and ramps. And when it crosses some threshold voltage, that generates a signal that tells the FET to turn off. So this whole thing down here is just a really complicated way of designing a circuit that will make the MOSFET stay on for a particular amount of time, right? This is just an on-time control circuit. So the MOSFET turns on, not because the microcontroller says turn on, it turns on in response to ZVS detection, and it stays on as long as the ramp timer allows it to stay on, okay? And so what is your control variable here? What do you get to control? You control ref timer, which is a voltage, but ref timer essentially controls the on time of the MOSFET. So this is an on time control thing. And the off time is whatever it has to be, right? The off time is whatever it has to be so for V switch to eventually come back down to 0, and this will just detect when it comes back down to 0. And I'm not going to go into how the NOR gate works, but if you analyze sort of the signals here, you'll see how it works.
So is there a delay added because of the two detector, because there are two stages here? Would it be same as if we would use a microcontroller? Would the delay time be same?
There is a delay time, and I'm glad you bring this up because this is what I was highlighting before, right? There are challenges with going to high frequency, and the faster you want this to go, this delay time better be as low. The delay time better be as low as physically possible. The delay time of these comparators is about 5 nanoseconds. Okay. The delay time of these logic gates is 2 nanoseconds, maybe 3. Okay. So the total delay through all of this plus the gate driver is maybe 10 nanoseconds, 15 nanoseconds. But it is a challenge. If you sent this through a microcontroller, God help you, you'd have a horrible, horrible delay, especially if there was any processing that you had to do.
Correct.
Now, if you can find a microcontroller with, a 500 megahertz clock and all of that stuff, like there could be a future. There could be a future where digital can do this. But today, because we're doing fast reaction time, it has to be analog. However, I will say this. How do you set this ref timer? This ref timer is basically the on time of the MOSFET, right? That doesn't have to react quickly. Right? That doesn't have to react quickly. It has to be changed, but it can be changed slowly. And so this ref timer actually is generated by a microcontroller. So we are using digital control, but the only thing the microcontroller does is it sets this voltage. And then this sort of funny circuit here takes care of all the quick reactions, right? All the fast reactions.
Yeah, very interesting. Yeah.
So the ref timer is varied by the microcontroller over the line cycle, which is a slow, right? It's a very slow time period. I don't know if I want to dig into this too much, but I have this slide here. If you analyze what the current is that the power converter is supposed to be drawing, right? This is a power factor correction converter after all. If you analyze the current that the converter is supposed to be drawing, so like the current right here where my little pointer is, you can analyze what that is, and you see that it's a function of course, the input current that you want to draw, plus you have to correct for the current that goes into the EMI capacitor. Most converters don't do this, and this is why they don't have perfect power factor. But because we're doing fancy digital control anyway, we might as well take this into account. And so I did a whole bunch of calculations, a whole bunch of math that's really boring, and you can calculate what is the on time that I want. For example, I think this is for FET-B. I think this is for the SB1, which is off screen. You can calculate the on time for what do you want it to be, right? To get power factor correction. And what's really cool, I think this is an amazing thing actually. The equation that you get is really cool. You get this expression, which is 2L IN over VN. And if you think about it, IN is supposed to be proportional to VN, right? And so this ends up being a constant over the whole line cycle. If you've studied boundary conduction mode boost converters before, you know that one of the advantages is you can use a constant on time over the cycle, right? And that term shows up here. I think that's the coolest thing. That term actually shows up here. That's that constant term for boundary conduction mode control. And then there's a whole separate term. This term here, X, by the way, is input voltage to output voltage ratio. I had to simplify that. But there's this term here that accounts for the resonance, right? Because we're not doing true boundary conduction mode, right? We have boundary conduction mode plus that little resonant time, and that throws you off. So there's this whole term here that just accounts for the resonance. If you had no resonance, for example, if CP were 0, this term would be 0. And then you have this final term that accounts for the input capacitance, right? This Cin is this EMI filter capacitance. And I told you before, you have to correct for that. So I think this is the craziest thing. I think this is such a cool thing that you get these three terms: the raw boundary conduction term, the resonant term, and then the Cin correction term. I think that's really cool. Okay, so we got this up and running. Okay, we built this thing. And so these waveforms that you're seeing up here, these are experimental waveforms. These are experimental from a scope that I just plotted in a nicer software. Okay, so these are my switch node voltages, B and A. You can see that they, like switch B, for example, this voltage comes down nice and smooth. And that's the inductor pulling current off. And then the switch turns on down here. So that's zero voltage switching. And for A, it's the same thing. Remember I said node A was supposed to ring up to V in, and then the switch turns on. You see this little glitch here? That's the switch turning on. And so you see B and A both getting zero voltage switching here for that turn on. And you can analyze all the other transitions as well. This is just an example of this ramp signal here, just because I did have a fourth analog channel. And then these are experimental digital. This is experimental digital data. Okay, so these were digital channels hooked up to the board, and you can go through and analyze how this works and see that all the signals go up and down at the right time. The only thing I wanted to show with this is synchronously rectified. So it is possible to operate this converter with the two switches as diodes, with two of the switches as diodes, but this is actually synchronously rectified. And it turns out that with the ZVS detection method that I have over here, plus just calculating the on time using those equations I had before, right? Just purely calculated on times, you can do a pretty good job of getting all of the stuff I said before plus synchronous rectification. It is possible. So here's a photograph. This is the same photo I had at the beginning of my PFC. The switching loops are actually underneath the capacitors, so you can't see those. These are my big buffer capacitors. These do not scale with frequency, unfortunately. It's a 600-watt converter. It's 98% efficient, which is competitive with even some bridgeless power converters. Okay, so this isn't even bridgeless yet, and it's already competitive with a lot of bridgeless converters. Power density is 80 watts per inch cubed. I'll show you a comparison for that in a second. But what I really want to show you here is just, in fact, yes, this is doing power factor correction. This is a nice, smooth sinusoidal waveform. There's a little bit of sort of glitchiness around the zero crossings. That's to be expected. But I'll show you in a second that the ratings for this are perfectly good. And I'm showing a dotted line here for V out being at 400 volts, but I will show you data for both 400 volt and 200 volt output voltages. So here's harmonics. Okay, so this has to do with the quality of the input sinusoid. And it turns out most of the time, like people always quote THD for quality of the input sinusoid, but it turns out that most of the time nobody regulates THD. What they really regulate is the harmonics individually. They regulate the third harmonic, the fifth harmonic, the seventh harmonic, and you're allowed a certain amount of each of those harmonics. But THD directly is usually not the metric. It's usually these harmonic limits that are defined by EN 61000, -3, -2, class D, right? Blah, blah, blah. But you can see, okay, so this is from 0 to 1. So what I'm taking is the actual harmonic content. I'm dividing it by the limit for each harmonic individually. So you can see that no harmonic violates the limit. They're all within the limits. And it's a little bit different if you have 220 volts converting to 400 versus 220 converting to 200 as the output voltage. But I don't think that's an inherent feature of the converter. That's just like if you spent enough time mucking around with the control, you could tune it up just right. But I have had limited time as a graduate student.
Yes.
I have even more limited time now, right? So here's data here's efficiency, power factor, and THD, if you really want to see it, although I just argued that neither power factor nor THD are regulated directly. It's really this thing over here. And this is for 220 volts RMS and different output voltages. Okay, so here's output voltage 400. So if you built this thing, this red curve here, you could expect 97 point something % efficiency, and you could drag and drop that converter directly into the same applications you were always using it in, because all of those are using boost converters with 400 volts output. However, If you are willing to redesign your system, you can use a 200 volt output, which again, I promise you will benefit that DC-DC stage, but it turns out it also benefits the power factor correction stage. Look at that nice flat efficiency curve.
Yeah.
And that's, 98% efficient. The power factor is well north of 0.99 pretty much always. And this is across power level. And that's for both cases. It's just a good power factor all the time. And THD bears that out, right? You're sort of under 10% THD almost all the time, which is well beyond what you need, because again, this over here is what you really need.
You took it up to 650 watts maximum?
For the 200 volt output case,
Yeah.
yes, I think, because the efficiency was high enough, I could do that, yeah.
Good.
I also did this for 110 volts RMS input. So if for some reason you only wanted to plug this into 110 RMS, or if you just want to have experimental data, of course, if you put the output voltage at 400 volts, you're going to have lower efficiency, right? Because you have a higher conversion ratio. And again, even if you knew nothing about power converters, you would guess that would probably cause your efficiency to be bad, and it does. I can put the output at 200 volts, and I'm still, keep in mind, for the 400 volt case, I'm only using the boost mode. I'm actually not using the modified boost or the buck mode, right? If the output voltage is 400 and my input is always low, I use the boost mode. If I set the output voltage to 200, I use the boost and the modified boost mode, right? Because I'm always using a boost mode, but I got to use the modified now. But because the conversion ratio is so much better, I get this consistent high efficiency. But if you knew that you were always going to plug into 110 volts RMS, if you were only designing this to operate basically in the US and Japan, you could even set your output voltage at 100 volts, right? And this is the performance that you would get. And here I'm using all three modes, of course. Power factor excellent, THD excellent. Okay. And I think we might be close to the end here. Yeah, I think this is my last slide, and just on time here. So this is a comparison between this work, which is right here in the middle, the star, and other converters. I have classified these by less than a kilowatt and more than a kilowatt. Those of us with experience designing these things understand that as you go to higher and higher power, you pay less of a penalty or an overhead penalty for like the control circuits and even the thickness of the PCB. Like if you're designing a 100-watt power converter, even the thickness of a PCB matters. So as you go to higher power, you expect higher density. So I don't know if it's entirely fair to compare this power converter with like some of these guys that are like 6 kilowatts. Okay. But I do have them on here, but I've just segregated them by power level. So I think these are a different category in my mind. Many of these operate at low frequency, and many don't include an EMI filter. So now imagine you have a low frequency and you have to filter low frequency, right? So if you included an EMI filter on some of these other comparison cases, their densities would be worse. Okay, so some of these densities are what they reported. I'm just reporting what they reported, but I imagine that their true density, if you actually included the EMI filter, would actually be less than that. So in my mind, I look at this and say, okay, that's pretty stinking competitive, right? It may not be the absolute highest efficiency you've ever seen, but it's among the highest efficiency power density combination, right? If you draw sort of a line here. So I think that's pretty stinking competitive. And then again, my secret sauce, right? The ace that I have in my pocket is the second stage, right? Almost all of these converters put out 400 volts. Only the ones that are circled are capable of putting out a lower output voltage than 400. They have some sort of buck boost capability. Okay, so only these ones are capable of competing on that metric. So if you compared this work with like 49, for example, right, again, my secret sauce, my ace in my pocket is second stage, right? If you built a whole system, I guarantee mine would win in that case. 39 is an interesting case. That's that 6, I think that's that 6 kilowatt case. So they're benefiting from the higher power. But yeah, anyway, so this is sort of the comparison to what's out there in the world, at least those that actually report power density. By the way, if you're writing papers, always report power density, please. For the love of all that is good, report power density, like, and put a photo of your converter. Just like it just makes sense. But anyway, of the people out there in the world who have published and actually reported their volume or their power density, this is the comparison. So I think this converter actually compares quite favorably to the competition. And so that's it. I'm done. Thank you.
Good, good. Spectacular presentation, Prof. Very good. Thank you for the explanation. Nitesh, please unmute yourself and go ahead. Nitesh? Yeah.
Yeah. Hello,
Please go
Dr.
ahead.
Alex.
Yeah, we can
One
hear you.
question. I saw your board. I was just trying to point out that what was the output capacitor? This big one was the output capacitor.
Yep.
Yeah. So here you could have further increased the power density. Suppose if you are anyway using second stage, so if the ripple is a little bit higher, and if you have tighter, you have faster control on the second stage, probably you could have increased your power density further, because this is the biggest component I see.
Yeah, so that's a really good point that you're making there, but I'm gonna quickly show you why that's actually not correct, because I have slides here from a different project that I'll show you here. Magnetics, blah blah blah, more magnetics. Nobody cares. Magnetics. Pretty sure I have it. Oh, here we go. Okay, here we go. So here's the thing with the power factor correction converter. The power factor correction converter is drawing sinusoidal current in phase with sinusoidal voltage. So if you look at the power that comes from the input, from the grid, right? The power that comes from the grid is pulsating, okay, up and down. And that pulsation does not happen at the switching frequency. It happens at the grid frequency, right? So this is 50 hertz, 60 hertz, or really it's 100 hertz or 120 hertz, right? Because it's really double. But this is happening at the grid frequency, the line frequency. And so the size of that buffer capacitor, this is for this converter, this is the equivalent capacitor for this converter. The size of that capacitor is not actually sized based on output voltage ripple. It's sized based on bulk energy storage from the grid. Okay, so it's sized to handle these pulsations, these very, very slow pulsations, not the switching ripple. So in fact, having a really high, going to high frequency actually doesn't help me here, and allowing for higher ripple on the output also doesn't really help me, unless I allow for higher 60 hertz or 120 hertz ripple. If I allow the 120 hertz ripple to be higher, sure, it is possible to go to a smaller capacitor. So you're absolutely right. If that's what you meant, then you're absolutely right. Magnetics, nobody cares, magnetics.
So you may have some disadvantage in your mind that suppose if I have higher, twice the grid frequency ripple in the output voltage, what would be the disadvantage for the second stage? Is there some disadvantage?
It depends on the second stage, right? But you're absolutely right. If you design a smart second stage that can handle kind of a really variable input voltage, right? That the output of this thing is the input to the second stage. Yeah, absolutely. If you design a smart second stage that can handle a lot of variation in that, then for sure, yeah, absolutely. You can reduce the size of these capacitors, as you're saying, and you get a benefit. So if that's an area you're working in, I think that's a very fruitful thing to be looking at for sure, is how do you make a second stage compatible with a wavy input voltage?
Yeah. Nitesh, does that answer your question?
Yeah, and this one thing that is just beside your capacitor, that is your inductor. Just out of curiosity, I want to know, like, this is the inductor or this
Yes,
is the inductor?
this is the inductor here. The power stage inductor is here, and then the EMI filter stuff is over here.
Okay.
This inductor, by the way, is ridiculously complicated. We wrote a whole paper on how to design this inductor. This is one of these I told you half of my group works on magnetics, right? So this was a whole, multi-year project of designing this inductor. So it's a whole other thing. Like, I can get into, if you got 3 more hours, I can get into that, but I'm gonna leave that for another time. But yes, that's the inductor.
So Nitesh, you can give your background to Prof so he knows what you're working on.
Yes, please.
Yeah, actually, I did my master's in from IIT Kanpur, and my thesis project was power factor correction. As of now, I am working with Philips Healthcare. So okay. I'm in the industry, so not much in the research, but yeah, this is the domain of my interest, and that's why I was interested.
Oh, fabulous. Yeah, I mean, if you want to talk more PFC stuff, absolutely, just shoot me an email anytime. I'm easy to find.
Good. One more
So,
question is, how are you sensing the inductor? I think this is referring to your analog control. How are you sensing your inductor current?
That's an easy one. I'm not. I don't. I sense, so here's what I sense. For doing the fast control, I sense just the switch node voltages. I'm just looking, I'm literally sitting and watching for ZVS, okay? And I'm watching the voltage directly for the fast control. Now, in terms of the slow control, right, there's a control that controls the current over the line cycle. How do I do that? It's totally calculated. It's based on the input voltage. If I know what the input voltage is, which I do because I can just measure that through a resistor divider. If I know the input voltage and I know the value of the capacitance, I don't actually have to measure the inductor current because I can say, I want my average input current to be such and such a value. Therefore, my on times should be X, Y, and Z. And it makes it happen. And the good news here, and so the reason I'm not using feedback, I'm using feed forward, right? The reason I'm not using feedback is you don't need that much precision, right? You don't need that much precision on the input current waveform. The input current can be, you can afford quite a bit of distortion in an input current waveform before you start hitting some sort of limits. And so I don't measure current at all, partly because why would you measure current if you didn't have to, right? I mean, it's lossy, it's difficult. I just didn't bother. So I never measured any currents anywhere in the system at all.
Yeah, maybe I got the question wrong. IL, I think they're asking about IL here. I think you just use a current probe. I think how you measured IL.
Yeah, okay, just for the experiment. Yes. Yeah, I'm just using a current probe. Yeah, just for experimental purposes. Yeah, just for testing it on the bench. Yeah, this is what a current probe. It's a Tektronix, like a 200 megahertz bandwidth current probe. I forget what the model number is, but yeah.
I think we are almost out of time. I have questions. What were the reviewer comments? Did they, anything significant that you can remember?
Oh wow, this was a while ago. Because again, you submitted it like I submitted it like a year and a half ago or something like that. Let's see. I mean, so the reviewers wanted to know, for example, like what these, like why this was distorted near the zero crossing. That was pretty easy to explain. They wanted to see more, like, so originally I had less data here. I didn't have all the cases, but I included all the cases in response to the reviewer comments. And that's actually, you know, a lot of times we kind of grouse about reviewers, right? Because like, oh, these reviewers asked me to do something stupid, blah, blah, blah. And don't get me wrong, I get that all the time too, right? I get reviewers asking all kinds of ridiculous things. But sometimes the reviewer is actually just trying to help you make your paper better. And so I do owe some of the things in this paper to the reviewer, to reviewers asking for things like, oh yeah, that's actually a really good idea. Like we should put that in there. But honestly, at this point, I remember very little about what the reviewer comments were.
And one more question. Obviously, you review papers as well, day in and day out. What do you look for in most of the papers in this area? Or is there any, when you skim through the paper, you're looking for these key points from the title and abstract?
So I mean, every reviewer is idiosyncratic, right? So I'm going to tell you just what I think, okay? If you're building a power converter for an application that is a very common application, like a power factor correction for like a computing thing, right? You have a million competitors, right? And so one thing I want to see in the paper is I want to see some evidence that your approach is somehow better than what's out there. And that takes one of two forms. It either takes the direct form, which is you better show me efficiency and power density that's better than everybody else's, right? That's the direct form. Or there's an indirect form, which is if you can show me that your converter has some feature that no other converter has. Now, if you said, oh, my converter has fewer devices, and that's a feature, right? I wouldn't actually count that as a feature because the whole notion of having fewer devices is just so you can have lower loss. And so if you have fewer devices and therefore lower loss, you better be able to show me that. However, if your converter has a feature like low output voltage, right, where it's hard to say like how that impacts efficiency and density, but it has some other benefit. You know, if you can show me some feature like that, or some argument that maybe it's going to have higher reliability, for example, or something, you know, but it's got to have some justification. You got to have some reason that this thing is better than what's already out there. And to me, that's such an obvious thing, but I read so many papers, I review so many papers where they're just like, hey, we had this idea and we built it and it works. And it's like, okay, but like, who cares? Like, why? Like, anybody can move any idiot can move some diodes around and come up with a new converter topology, right? We've got to show that it's better somehow than what's out there. And then the other things I look for is like, I mean, I mentioned it before. If you're building something and your argument is this power converter gets better efficiency or better density, or both, report the density, right? Report the power density and give me a photograph, kind of like this one. Actually, even better than this one would be one, looking lengthwise and one looking, a top-down view and a lengthwise view, so you can show me all the dimensions. It drives me nuts. I have students do literature reviews. They'll go read, or skim, really. They'll go skim 100 papers.
Yeah.
They'll go skim 100 papers to try to figure out, okay, what's our competition, right? What's the state of the art? And out of those 100 papers, maybe 6 or 7 of them report power density. It's crazy to me. I can't understand it. And I also don't understand how the other 94 papers got published in the first place. And by the way, even if you're telling yourself, well, I'm not really targeting power density, I'm just targeting efficiency, guess what? Efficiency and power density trades off with each other. I can make any converter in the world 100% efficient if you give me enough volume. Okay, so it's never fair to just report efficiency and not power density. That's never, ever a fair thing. So I can't imagine a scenario where you wouldn't want to report power density. It's just good practice. So I look for that, and it's different for like magnetics papers or like EMI papers, but when you're talking about building a power converter, I always ding people if they don't have power density in there, and I will not vote to accept the paper until it's in there. I'm just one man though, unfortunately.
Okay. I have one last question.
Hopefully that answers your question.
Yeah, one last question. Obviously, sure. You have been reviewing papers for quite some time as a doctoral student as well as a professor now. So what landscape shift have you seen in the area of power electronics from the time you started doing literature review now that you're reviewing? Is there any significant shift towards one technology or anything significant?
Well, so like obviously wide bandgap is a huge thing, right? I think people are starting to embrace going to higher frequencies, and by higher, I mean in like this power factor correction stage, I would mean in the hundreds of kilohertz, beyond 100, right? Into the 500 kilohertz or pushing a megahertz. I forgot to mention this power converter is operating at 2 to 3 megahertz. It's a variable frequency converter, but it's 2 to 3 megahertz of operation. So I see people embracing high frequency a little bit more. I see them encountering a lot of the problems that some of us have already been encountering for a while because we've been pushing this area forward. And magnetics being a big thing. I see things moving more and more in the direction of magnetics being a big bottleneck, which is part of why I've organized my group the way that I have. I see a lot of people using wide bandgap devices really badly in the sense that they take a silicon converter and then they drop wide bandgap into it and they're like, oh, look, it's better. And somehow they get that published. I don't know what kind of idiot reviewers are passing those papers, but don't do that, right? Like if you're going to really take advantage of GaN, like go or silicon carbide for that matter, start looking at getting some soft switching and stuff like that. I mean, don't get me wrong, silicon carbide will be better than silicon in a hard switched application, but why not move to the next thing? Yeah. So I see a lot of people interested in electrified aircraft these days. That seems to be a big kind of application area. I've seen 1.5 million high step up converters going from like 10 volts to 200 volts or 20 volts to 400 volts or something like that. In fact, I've seen so many of those, I'm almost like, it's kind of this thing where once I've seen it 1 million times as a reviewer, it's a dead field, right? It's like, it's a dead area. So it's almost like, I'm telling you the things not to go into almost. I don't know, this is just a few things off the top of my head. I'm sure if I thought about it for a while, I'd think of some other things.
Yeah, I think one last question. Nachiket, please go ahead with the question and we'll wrap up. Nachiket, please unmute yourself.
Professor Alex, I hope you are able to hear me.
Yes,
so
yes.
The question is regarding the wide bandgap devices and use of GaN in the present topology. So GaN has very poor reverse conduction characteristics, and we would like to reduce the dead time to the minimum possible. So will it be possible to do that with this present analog control technique is my question.
Yeah, actually that's something that I rather like about this converter is every single switch, all 4 of them, turn on in response to these ZVS detection signals. So that includes, okay, so I spent a lot of time talking about these two switches, SA1 and SB1, and how the resonance brings their voltages to the right space so they turn on the ZVS and all that stuff, right? But I'm also using these same types of signals for SB2 and SA2. So let's look at one for example here. At this location that I've labeled I1, okay, this is where SA1 and SB1 were on. The inductor current was ramping up, and then I turned SB1 off, okay? So this isn't some slow resonant thing. This is a whole bunch of inductor current pouring into this node and really quickly ramping that voltage up. Well, guess what? My fast ZVS detector is watching, it doesn't just watch that voltage go down, it watches that voltage go up too. And I have the same step down, but I have a different ZVS detector that is not detecting when does this voltage ring down to 0, it's detecting when does this voltage slam up to V out. And so SB2 turning on, which is right here, SB2 turning on is also in response to a 0 voltage switching condition or a 0 voltage switching detection. And so in principle, my dead times are neither longer nor shorter than they need to be. They are precisely what they need to be, neither more nor less. And that's by design, right? It's because SB2, just like SB1, turns on because it watches its voltage come up to 0. You know, the voltage across SB2 goes to 0. And then it turns on in response to that. So you're absolutely right though. Using the body diodes of these GaN FETs is miserable. Oh, what a horrible way to die. So yeah, absolutely. You want that dead time to be ideally a little bit too short. If anything, you want it to be a little too short because you'd rather miss ZVS by just a little bit than have that diode turn on because that's nasty. So yes, that's correct.
Okay.
Yeah, great intuitive explanation, Professor. Thank you.
Fabulous.
Thank you, everyone. Thank you, Prof. It was really incredible and great to see the passion pouring out. The explanation was really good. I hope it benefits all. And I thank you for your time. It was really great explanation.
Thank you very much. It was a pleasure. It was my privilege and my pleasure to meet everyone and to have the opportunity to speak to you today. So thank you so much. I appreciate it. And anyone on this call, absolutely feel free to just shoot me an email. And like I said, I'm easy to find on the UTexas StudyDU website. I'm also on LinkedIn, although emails are probably best. So yeah, feel free to reach out if you have any questions about what I talked about today or just about what I work on and so on and so forth. So yeah, thank you.
Yeah, we hope to see great things from your group, Prof. I think it will grow very well in the coming years. Yeah. Thank you, everyone. So yeah, we'll end the meeting. Yeah.
All right. Thank you. Bye-bye.